11.3 talks about members composed of two or more components. Actually, 11.3, and well, yeah, that whole section. It talks about different situations, though. The first situation they talk about is referred to as in series, or if you will, stacked forces, where they're acting all on something at the same time. Two different composites, or two different components, which makes a composite, right? So we have to look at that. There's an example there. Here's a picture of that, and the force is acting on both of those components. So what do we have? And we can have different situations here. Now the one on that we're showing here right now is unrestrained. The one in the book, figure 11.7, will be restrained, so we'll look at those. The first example they give you there on page 227, example 11.10, says assume components A and B are as described in table 11.2. In other words, one is an aluminum alloy, the other one is a gray cast iron, and it's got the different conditions, if you will. It shows you the area, the length, the modulus of elasticity, and then the thermal coefficient. So it shows you those materials and some information from Appendix G. It says the supports are unyielding. There is no initial force in the two-component member. Screen keeps flashing. Determine the stress in each component of the member when the temperature rises 20 degrees Fahrenheit. So there again, there's that table 11.2 shows you the different information there, and I don't know if I captured that here or not. Looks like I might have. That's it right there, isn't it? So we'll share that. Just whoops, I didn't need to do that. Sorry about that. Put that up there, and we'll have that to look at. So what do they tell us to do? Well, it says consider two steps: unrestrained expansion followed by the application of sufficient force P to restore the member to its original length. So it's a two-step process here. The first step in the unrestrained expansion, we're going to use the equation from page 223, 11.3, where it is deformation equals the deformation of the aluminum plus the deformation of the cast iron. Okay, so that's not the actual equation. The equation we're going to use is and they draw it out here, alpha, which is thermal coefficient of expansion, right, times the length times the change in temperature of each one of those components. That's for the aluminum, plus same thing for the cast iron. And we add those up. So I think, did they give us all the information there? I think they probably have, haven't they? So this is kind of just a plug them in there. So we're looking at 13.1 times what? 10 to the negative 6th. Over 1, or 1 per degree Fahrenheit, times the length, which was 60 inches, and the change in temperature. It gave us that 20 degrees Fahrenheit, plus coefficient will be different here. We'll want 5.9 times, I'm assuming 10 to the negative 6. Yep. And then we've got length on that one is 18 inches divided by, or excuse me, times 20 degrees Fahrenheit. Now, what I would suggest you do is you punch all those numbers in your calculator right now and make sure you get 0.1784 inches. So with all those conditions, that's how much that's going to move, how much that's going to deform. 0.0178, and the one piece was what, 60 inches, and the other one was 18. So it's moving about 18 thousandths of an inch. Again, make sure you can punch those in there. If you can't, then you need to figure out why you can't. Easy enough. I mean, because then if you have all the numbers correct come test time, you should be in pretty good shape if you can do this. I mean, but if you can't get it replicated here, then you need to know why. Now, so that just tells you how much it's going to move based on those characteristics of the material. Then we've got to figure out what kind of force is going to be applied to do that. So we're kind of working backwards here, aren't we? So that part of it is equation 910 from back in chapter 9, where we used the modulus portion of that to figure out the deformation. So this, if you will, was part A, and this is going to be part B. And there, the deformation equals what? The force times the length over the area times the modulus of elasticity of the aluminum plus, same thing, force times the length over area times the modulus of the cast iron. Then that has to be rewritten because we're looking for P, aren't we? We're looking for the force. So we have to rewrite that. So look there on that page, that gets rearranged so that we've got the force equals what? The deformation over this big mess, the length divided by the area times the modulus, and this is for the aluminum, plus, same thing, the length over the area times the modulus of the cast iron. We know the deformation now, right? 0.01784 inches divided by, well, we got the length of, for the first one, we've got a length of 60. The area was given as 6 square inches. And then we were given the modulus of elasticity, 10,000 kips per square inch. Plus 18, 8 square inches, 15,000. So note they said, so what do we get there? We end up with a P of 15.0 0.51 kips. Again, put that in your calculator and make sure you can get that. Or what would that be? That's 15 point, right? It's not a comma. So what, 15,510? Or would that, no, that'd be more than that, wouldn't it? 155. Thousand. Pounds. But they left everything in kips.
10,000 and 15,000 are kips.
Right. Everything was kipped. So this down here really, you don't really have to worry about that because it's left in kips the whole way. And I guess, and the reason they did that, they gave you the modulus of elasticity and kips from the get-go. So, from the start. So then what? It says calculate the stresses then. So that's the force that's being applied to make that change, that 18 thousandths of an inch. So calculate the stresses. So the stress in the aluminum, or like I said, they're using the S, is what? The force over the area. So we got 15.51 kips, and the aluminum we had 6 square inches, right? Yep. So we're looking at 2.59 kips per square inch. Stress in the cast iron, same thing, force over area. Still got 15.51 over 8 square inches, right? 1.939 kips per square inch. So it's a composite deal here. It's got one force acting on it. What kind of stress is it building up in each of those components? And that's the stress that's being created in each of those components. Okay? And that is an unrestrained condition. So anything can move there. Questions? Shouldn't be too bad. I mean, we're getting to a point now where it's just making sure you use the right equation. In some cases they're being rearranged, but you can go in and you'll have your book, right, come test time, so you should be able to find the right equation without too much difficulty, and then punch the right numbers in and make sure you can punch them in your calculator. If you can't, then you'll be in trouble. Well, then the next example problem they give there is where we've got, it says this is another type of member composed of two different components, but in this case the components are in parallel. So it's an example they cite here is a column composed of a steel shape encased in concrete. So they both have to be able to act on that, or the stress is going to be acting on both of those materials at the same time, right? So you don't want that. If the stress is too much on the concrete, then your concrete's going to break out, isn't it? So you got to be careful of that. So it says for the same deformation, the stress developed in the material with the higher modulus elasticity will be greater than the stress developed in the material with the lower modulus, assuming the two materials are of the same length and deform equally. So they're talking there, they've got,